Hello everyone, welcome back. Now that we have the background of theory in gas dynamics and also in computations, basically CFD, let us try to solve some problems. Okay, we have already solved using simple 1D codes, but let us see how we can use some of these open source codes or even commercial codes for that matter. So, as we have discussed earlier in CFD, we have 3 steps. One is the pre-processing, right. So, one is the pre-processing where you basically make the grid. Okay, first you make the geometry if you have, or you can import the geometry from somewhere. Okay, and then you make the computational domain. Okay. Then you make a grid in the domain. Okay, and there are certain rules for making grids, as we have discussed earlier, that you may have structured or the unstructured grid, but you have to respect the boundary layer on the wall. Okay, you have to resolve the the flow near the wall. Okay, so all those kind of things, also near the inlet and outlet, and maybe in the top and bottom, you have to create a grid that respects the boundary condition that we have there. Okay, so that is pre-processing. Then we have solving. Okay, the solving, you have to set up the solver. Okay, what kind of solver you want to use, what kind of scheme you want to use. Okay, and then what is the time step that you want to use. Okay, what is your convergence criteria and all those kind of things. Okay, so this is the most important thing, how to set up the solver. Okay, and depending on the solver that you are using, you will have several buttons to choose what flux scheme, how do you want to reconstruct it, the flux scheme for inviscid, for viscous, okay, the time marching scheme, implicit, explicit, first order, second order, third order, and so on and so forth, right. And finally, you have the post processing. So, once you have done the simulation, okay, and let us say you have received the convergence that you want, okay, then you need to basically plot, let us say, the contours or the vorticity, whatever variable that you want, the contours or streamlines or velocity vectors, isosurfaces, all these kind of things you need to plot. You may have to make the line plot to, let us say, visualize what is the wall pressure or the flux on the wall, and so on and so forth, right. So, what I will do in the next few minutes is basically I will first show you basically what are the options that we have in let us say in Fluent and OpenFOAM. So, these are some of the most popular solvers. One is commercial, the Fluent and Fluent, and second is OpenFOAM, which is the open source solver, right. And but this does not mean that I am saying that this solver is better than some other solvers that we have. It's just that these are the popular solvers and many of you might have already used it. Okay, but there are several commercial and open source solvers in the market that you may like to explore. For example, in terms of commercial solvers, you have say CFD plus plus, star CCM plus. Okay, then you have Cadence Fidelity, and I think Altair also has a CFD software. So, there are many several actually commercial CFD softwares. Okay, and they all have some specialized schemes and may be good for certain thing. Okay, let us say some are good for turbo machinery flows, some are good for high speed flows. Okay, some are good for low speed flows, some are good for multi-phase flows, and so on and so forth. Okay, so depending on the problem, you might want to choose. Similarly, in the terms of open source solver, so OpenFOAM is one, but you have, for example, SU2, which is good for, let us say, if you want to do commercial, not commercial, the compressible flow problems. Okay, you have XCompact 3D. Okay, and there are actually many more solver. If you just go and search for open source CFD solvers, you will find many of these, because the name itself is open source. So, basically you have the source code available, but the responsibility lies on you that how to set up the solver. They may not have extensive validation cases. Okay, they may not have a very good user manual because they are open source by the name. Okay, so you have to be good in CFD to basically the theory of CFD to use them. And for commercial solvers, they are well validated, and there has been there is a team working on that, dedicated team to basically ensure that everything works as expected. Okay, and they would give you limited options, but very robust options, okay, which will work on your problem. So, that is the beauty of the commercial solvers. Okay, as I mentioned earlier, I am not advocate of any of these. Okay, you can use whatever you want. Okay. In fact, I, for example, use many of the solvers that I have developed in house, okay, in our group. Okay. So, yeah, for example, let us talk about the solver schemes. Okay. So, one thing is the flux scheme that you choose, but as I mentioned in the mentioned earlier that OpenFOAM does not have many flux scheme based solver, because it is primarily a pressure based solver. So, we will look at some of the schemes used for the gradient and let us say reconstruction kind of thing. So, the gradient is now if you want to use the calculate the gradient, you have like, so both are this finite volume based solver. Okay. So, OpenFOAM and Fluent both are finite volume based solver. Okay. So, you can use unstructured grade for both of these. Okay. So, in Fluent it is called gradient option. In OpenFOAM you will have to go basically go and modify the file. I think it is FB schemes, okay, where you have something called grad schemes, and against that you have to specify what kind of scheme you want to use. So, popular schemes are least squares and green gauss. So, we have discussed this when we were talking about the finite volume gradient calculation. So, we have to go from, say, let us say cell center to the, I mean you want to calculate the gradient at the cell center and the phase center for the viscous flux. So, how do you calculate that? So, that is what it is, the grad schemes. And in OpenFOAM we call it like divergence schemes or DV schemes. In Fluent it is the convective scheme. Okay, there you can choose like basically it's basically kind of reconstruction. Okay, so whether you want to take upwind or second order or weak or muscle, that kind of thing. Okay, and finally you have the viscous part also, like you have del square u and so on and so forth, right. So, that is governed by the Laplacian scheme in OpenFOAM. We call it Laplacian schemes, but in Fluent it is by default I think they use basically the second order central differential kind of scheme, okay, by default. So, you do not have to choose that, and the reason for that is, as we have discussed earlier, that we have seen that the elliptic equations or equations of this kind of nature, okay, the diffusion equation, okay, so they are stable to the central differential schemes, whereas the convective equation. So, if you have del u by del t plus c del u by del x, okay, let us say equal to del t u by del x square, okay, let us call it mu. Okay, so, this part you can use the central differential, but here you have to be very careful because this represents an hyperbolic system, right. So, in Fluent this part will be kind of inbuilt, and for this you have to choose the scheme, you have a choice. Okay. Yeah. So, in OpenFOAM you have options like orthogonal. So, if you have a nice orthogonal mesh, then it is fine. Okay. But if you have, let us say the meshes which are kind of skewed or I mean it is not proper orthogonal, then you have to have option of corrected, okay, or limited is basically between orthogonal and uncorrected. Okay. So, how much you want corrected you want to give, I mean how much. So, you get the you use this orthogonal scheme to calculate the Laplacian, but then you have corrected because the grids are not basically organized like this. Okay. So, you can have grid like this, like this, like this. Okay. So, how do you calculate this viscous part, right. So, then you have phase corrected and linear feed, and there are several more options. Okay. I will not go into details of each of these. Then apart from this, we also have two more things which you can define in the FB scheme. So, this is called FB schemes. We will shortly see it, okay, in OpenFOAM, right. So, in which you can find the gradient option, the grad scheme, divergence scheme, Laplacian scheme. And also we have, for example, the interpolation scheme and the SN grad schemes. Okay. So, interpolation is like how do you go from cell to phase. Okay. So, whether it is linear or upwind or linear upwind. So, upwind is basically it is 0th order, linear is you linearly go from the cell to the phase. So, if you have cell here and cell here and you want to get the phase here, you just take the average of this. Okay. So, that is the linear scheme. Then you have linear upwind, okay, so which is high order scheme there. Okay. Then we have SN grad scheme, which is the surface normal gradient scheme. So, how do you calculate the surface normal? So, if you recall, we have this n cap or n hat that you need to basically find out. So, how do you get this surface normal? Again, these are the phase normal gradients, and it depends on what kind of phases you have, okay, because it is a general purpose solver, you can have unstructured grid. So, depending on that, like we had this Laplacian schemes, you can have, if you have a nice orthogonal mesh, then you do not have to worry, uncorrected is fine. But if you have a the complex unstructured mesh, then you have to choose either corrected or limited kind of scheme, right. So, these are the solvers scheme. Then as we discussed earlier, then you need to have limiter. Okay, if you do not have limiter, then the solution will start showing those Gibbs oscillations, and it may ultimately diverge or blow up, right. So, we have like both the slope limiter as well as the flux limiter options available, and they are in both OpenFOAM and Fluent. Okay. So, they call it as cell limited or limited linear. Okay. Then we have the reconstruction. Okay, reconstruction also we have this muscle scheme, I mean the linear appointment that we mentioned earlier. Okay, and yeah, I mean in terms of like if you have a sock and the socks are basically at very high Mach number, then normal pressure based scheme that we discussed earlier, they may not work. So, the only scheme that you have which are basically flux test based scheme in open form is this Kurganov Tadmor, okay, which is basically upwind based central differentiating scheme. So, central differentiating by itself is not stable. So, there is some upwind bias is there, right. So, that is the only scheme that we have, but of course, there are new implementation, user based implementations are coming up in terms of EOSM or HLLC. Okay, in Fluent you have more choices because you have basically specific density based solvers. Okay, you can once you start Fluent, you can choose either the pressure based solver or the density based solver. As soon as you go to density based solver, you can choose like rho or HLLC or ASM, actually it is ASM plus. Okay, so you can choose these kind of schemes. Okay, then in terms of time schemes, okay, in open form for example, you have Euler, backward, Crank-Nicolson. You can also implement your own scheme, for example, Runge-Kutta 3, Runge-Kutta 4. Some of them are actually already there, and a similar thing you have like first order implicit, second order implicit, or maybe the blended second order. So, they are there in the Fluent. So, there may be slight difference in terms of implementations, okay, but what I am trying to give you is the big picture of what are the schemes which are available in both these solvers. Okay. Yeah, so let us say you want to set up simulation in open form, right. So, what are the things that you need? So, first you need to basically create a grid or you need to import a grid from somewhere. So, open form allows you to basically import grid from many grid generators, either commercial or open source. You may create a grid in let us say ICM CFD, okay, and then you can import it here, or you can create a grid in point wise and import in open form, right. Or you can use inherent grid generator in open form. For example, there is a grid generator called block mesh, okay. It creates a nice structured mesh, or if you have like say you have something called snappy hex mesh, okay. So, these are the snappy hex mesh, yeah, these are the grid generators available in open form. Okay. This is for basically complicated geometry domain. Okay. So, if you look at open form, if you look at any of these simple solvers, so open form has several solvers. Okay. They have, as we discussed earlier, we have like simple form, okay, pimple form, row pimple form, ICO form, okay, row central form. So, they are some solvers designated for different kind of problems, okay, but one solver can work for maybe many different problems, right. So, if you look at the directory structure, you will have three main directories. One is 0, okay, another is the constant, and the last one is the system. Okay, you have to have these three directories, otherwise it will not run. Okay, and in the 0, if you see, you have the minimum thing that you need to do is basically the pressure, temperature, and velocity. If you are doing compressible, if you are just doing incompressible, then just pressure and velocity is enough. Okay, if you are, you may also have like pressure and density and u. That is also fine. And then the P equal to, you can use P equal to RT and T will be calculated. So, either you can specify T or rho and pressure, right. So, this is 0 folder means what is the I mean what is, how are you initializing, okay, that is what is basically 0 folder. But in addition to how you are initializing, it also, I mean you also need to provide the boundary conditions. So, any domain that you have basically internal values, whatever values that you have, and then you have some values at the boundaries which usually do not change, okay, or even if it is changing, you need to specify that how it is changing, it is usually specified, okay, unless it is let us say supersonic problem that we discussed, that it is extrapolated. So, that also you need to say okay, you need to extrapolate it, okay. So, you need to specify for every single phase that you have, let us say this is 1, 2, 3, 4, for every single phase you need to specify what is the boundary condition. Also you need to say that what is the values at the internal points. So, and how, I mean those are basically the initialization point in the beginning t equal to 0, what are the values that we have, okay. Then important thing is in the system you have something called block mesh dict, okay. So, this is for example, if you are not importing a mesh from elsewhere, but you want to construct your own mesh, then you will basically define a block mesh dict, which is dict is a dictionary file, okay, and you will specify the coordinate points and how these nodes are basically connected to one another, whether it is creating I mean different blocks or single block and all those kind of things, right. So, that is the block mesh dict. So, and then you will have control dict. This is a very important file. where you will specify what solver you are using, what is the delta t that you are using, whether you are calculating based on CFL, whether you are calculating, you are keeping it fixed, okay, when you want to save the file, what is the file format that you want to save, all these things will be specified here. Apart from that, you can have many of your own functions. Let us say you want to extract a line. So, this is my surface and I want to extract all the values on this line at every time step, that also you can do. You want to write a probe at certain point, you can get the probe data. Okay, so, all these things can be written in the control deck. Okay, these are two important things. So, basically FB schemes and FB solution. Okay, so, we will discuss this shortly. I have already discussed about FB schemes, okay, and then we will also see the FB solution file. And this is set fields dot dict. Set fields dict is basically, let us say you are trying to initialize certain condition. Let us say you want to solve a short shock tube. So, you have some values on P, T and U. So, you have made a grid and then you want to say that okay, my if x is less than 0.5, then you have certain value of P, and if x is greater than 0.5, then certain value of P 2. Okay, similarly, rho 1 and rho 2. Right. So, that you can set in set field dot dict that okay, if it is less than this, you use this value, otherwise use this value. Okay. So, it is not I mean this file is not necessary for all simulations, but some simulations where you want to basically after you defining or making your domain and the grid, you want to specify some initial condition, some specific initial condition. Let us say you have a shock which is impinging on a wall, okay, and you want to start with basically this is the pre-shock condition and this is the post-shock condition, and you want to see how it develops, right. So, you have to in the grid you have to specify all these things. So, those things can be set up using the set fields dict. Okay. Yeah, so, this is for example, file of a block mesh dict. So, I have defined, so I am basically showing the system files, okay, and this I am trying to solve problem short shock tube. So, I want to take that example first because we have already discussed and we know what the problem is. So, I want to solve that problem using OpenFOAM. So, one important thing is OpenFOAM is a 3-dimensional solver. So, even if you are solving a 1D problem, you have to make a 3D grid or 3D domain, which will look something like this. Okay. And then you can say, okay, I only care about, let us say you can have this empty boundary condition on left and right and top and bottom. Okay. What does it mean is that it will not solve on top and bottom and left and right. So, let us say if you do not solve left and right, okay, basically on the spin y direction, then you are solving a 2D problem at the center, right. If you are for example, you put this also top and bottom also as empty, then it means you are solving just one line along a line. So, we will show you that example. Let us say the short shock tube is so 1D problem, right. There are some values of P 1 and rho 1 here and P 2 and rho 2 here. Okay. Your velocities are 0 on both the sides, okay, and then the diaphragm burst at T equal to 0, okay, and then the shock tables on this side and expansion tables on this side. So, you can solve using 1D problem. You can also solve using 2D, but it will not necessarily be very expensive, okay, unless you are interested in what is the effect of wall, then you have to put wall boundary condition on top and bottom, okay, or you can solve in 3D also, then you have to basically extract a line which is at the center, okay, and then you can make a 3D grid. Okay, so, this is for example, I have made this 8 points, okay. So, this goes for example, x goes from -5 to 5, okay, this is -5 to 5, okay, y goes from -1 to 1, okay, this is -1 to 1. Okay. So, this is x and y, made a grid like this, and then z go to basically -0.1 to 0.1. So, this is the grid that we have. So, this is the domain that we are making by creating these points. Then I have to say about the connectivity. So, this is my 0, 1, 2, 3, 4, 5, 6, 7. So, it can be like, so this is -5, -1. Okay. So, basically these 4s are connecting one of these. Okay, and then you have these 4 connecting on the back side of face and they are all connected. So, this is the hex kind of grid, okay, and then I am saying on the x I have 300 points, y I have 300 points, okay, this is 300 points here, 300 points here, and z I am just keeping 1, that means I have to apply the empty boundary condition. So, this is a kind of 2D problem. This is a grading, simple grading. So, basically I am not giving any bias in the grid, okay. So, then you have to define that what are the sides, what are the faces that you have, okay, faces are basically the boundaries, okay. So, you have to name all these boundaries so that you can apply the boundary condition in the 0 file, okay. This is empty. So, there are 2 faces which are empty, which are in the spin y direction, in which I did not specify any grid. So, it is a 3D problem, but I am solving in 2D. So, you have to give this, define these names as empty, okay, and type as empty, so that you can specify the empty boundary condition there, okay. So, yeah. So, now regarding let us say you want to solve the problem of short stock tube, right. So, what is the condition that you have? You have P 1 is equal to 1 and rho 1 equal to 1 and P 2 equal to 0.1 and rho 2 equal to 0.125. Remember this is the short stock tube problem. So, you can basically take R equal to 287.4 and get calculate this T 1 equal to 0.00348. Similarly, T 2 you can calculate from this P equal to rho R T, okay, which will be 0.00278. So, this is the set field strict. What I am saying is that, okay, in this box, okay, you set the value as 0.00278, you can say that it starts from 0.5. Okay. So, and the pressure value is 0.1, else you keep pressure equal to 1 and temperature equal to 0.00348 and you will stay 0 anyway everywhere, right. So, this is what we are saying, that half of the domain is like this and half of the domain like this, that is what the set field strict does. So, as soon as you start, it will basically copy in the 0 file and it will basically accordingly replace the values and the corresponding points with the values here like this or like this. Okay. Now, this is very important, the thermophysical property, that what kind of mixture you have, okay, the transport property. So, here it is constant, but you may have basically the Sutherland's law kind of thing. Okay. Basically, how to calculate the viscosity. Equation of state we are using perfect gas, but you can also use non-perfect gases. Accordingly, to write the equations. The energy, as I mentioned, that you can solve the internal energy or total energy. Okay. So, all these possibilities there. Okay. There are infinite possibilities in open form. Okay, depending on the problem that you have. Okay. Mixture you can have basically the pure mixture, or you can have maybe mixture with some things which are changing. Let us say you have solving a combustion problem kind of thing. Okay. So, this is air. So, molecular weight is 28.96. Okay. This is the Cp and H. Okay. Now, this you can see that I put the mu equal to 0, that means the viscosity is 0. So, I am solving an Euler problem. Okay. Simulation type is laminar, but my viscosity is 0. And Prandtl you can set 0.71 or 1 does not matter, because we are solving a Euler problem like we did earlier, there is no viscosity here. Okay. So, these are basically some of the bonding conditions that we have. Okay. So, this is for example, pressure, this is very important, this is the unit that you have. Okay. So, you have to check the unit. So, this should be a Pascal. Okay. This is basically mLT. So, this is mass, length, temperature and some other things. Okay. So, there will be the fourth one is the temperature. So, this is T is the temperature here. Okay. This is meter per second. So, yeah. So, mLT, the T is the time here, T is the time and this is the temperature. So, you have to check the dimension consistently. Why I am telling you to check the dimension consistently? Because if you go to, let us say, pimple form or any incompressible solver, okay, pressure based solvers used for incompressible. So, then you will see that instead of P you define P by rho there. There is no separate T file or rho file, but you define P by rho. So, accordingly the unit changes. So, accordingly you have to specify what should be the value here. It is not P, but P by rho. Okay. So, many students make this mistake. So, if you are using pimple form, it will be like this. Okay. And if you are using, let us say, rho central form, okay, then it will be just P. Okay. And why is that? Because in incompressible we say the density is constant. So, that is how the code has been written. Okay. And I am saying that the sides are basically 0 gradient and type is empty, means we are not solving on anything there. Okay. Similarly, the temperature. So, these are the internal field. So, this will be overwritten by the set field directory dictionary. Okay. And same thing in the velocity, you have everything 0 0 0. Okay. So, let me go a little bit fast. So, let us say if I am trying to solve a 1D problem. So, what I am doing is basically just 0 1. So, we have something from 0 to 1. Okay. You can see that this is 0 to 1. Okay. Every side is 0 to 1, but then what I am saying is that my 4 faces are empty. Basically, 4 faces I am converting the 3D solver to 1D solver. Okay. The 4 faces are empty, these 4 faces are empty, only one faces are type of patch. Okay. So, which will be solved. So, basically you can think that my top and bottom both are solved empty, and this, okay, the sides are solved empty, only this is the patch basically where we are solving the problem. So, we are reducing the 3D problem to 1D problem, and accordingly you can see that I have given only 5000, I mean I have given 5000 point in the x direction, but I have given 1 on 1 in the y and g direction. Okay. So, if it is x, y and z, so y has just 1 point, x has got 5000 points and z has got 1 point. So, if there is empty and then you have problem being solved in this x direction. Okay. And we have given 0 gradient here and here. okay, at the extreme boundaries in the 1D flow. Okay, you can see this is the 0 gradient, right. This works because we are simulating till time where the shock does not cross the right hand side. Okay, if the shock, so this is your domain and you started from 0.5 and let us say you want to go to 1, okay, 0 to 1. So, we are solving till time till it does not basically go to this point. We are basically seeing what happens at, let us say, t equal to 0.2 or 0.3 as we have seen earlier, right. So, this is a typical situation where there is shock here, expansion here, and then you have a contact discontinuity somewhere here, right. Yeah, so if you are using, for example, the contradict, if you are using a row central form, okay, then we have said the solver as row central form starting from 0, the start time at 0, end time is this, okay, you are solving let us say 0.01 and 0.2, 0.4, okay, this is your choice. This is starting delta t, okay, but you also specify what is the maximum delta t, okay, what is the maximum Coulomb number. This you can see that my Coulomb number is very small, just 0.2, because using row central form. This is a central differencing based scheme, although it is upwind bias, but it still allows very CFL number, and your delta t needs to be calculated based on the Courant number. So, that is why I am said adjustable time step as yes, okay, and this is when I want to write it. Okay. And then you have flux scheme, I have sent Kurganov, there is also a scheme called Tadmore, but you cannot use Tadmore for let us say short circuit problem. So, Kurganov is a better scheme, and then this is what I discussed. So, dy dt scheme, the time matching scheme, the grad scheme, the divergence scheme, the Laplacian scheme, interpolation scheme, and grad scheme. Okay. So, you can see for example, for all of these u, e, and this will not matter I think k, because we are not solving a turbulent flow problem and all, right. But otherwise you can see that I have chosen Gauss upwind. You can play around with this scheme. These are very critical, that you should choose a correct scheme, so that you are not compromising on accuracy, at the same time the solution does not blow up. Okay. Here you can see Laplacian is Gauss linear corrected. Okay. Then we have von Leer, use the vectors of von Leer V is the vector implementation of the von Leer for the vector fields like u. Okay. This is for the calculate the gradient. Okay. And then this is the FV solution. So, we have 3 equations, rho, rho u and rho e. Okay. So, we are solving a diagonal based solver here. Okay. You can go and read about the details, what does diagonal mean. Okay. And these are the solutions that I have, okay, using the row central form. I will share these files with you. Okay. So, this is the exact one, and then you have the row central form, and you can see that the match is quite good. You can see little bit, I do not know if you see or not, there is a certain blip here. Okay. So, because of the contact discontinuity, if you further reduce the time step or maybe refine the grid further, okay, you will see that this will kind of disappear. Okay. Yeah, you can solve the same problem with row pimple form. So, here the time is you can see the setup is different. Row pimple form is also an unsteady solver, so that is why you can use it. Okay. Row simple form you cannot use, because you need a time accurate solution in the short circuit problem. So, here you can see that I have increased the maximum Courant number to 0.5. In fact, you can use a much bigger delta t, you can see delta t I have used 1 e minus 4, right, and I have said that adjustable time step is no, that means you have fixed the delta t, and you can see it runs for that. And here you can use different kind of divergence scheme, grad schemes. Okay. I mean this is all as you start using the solver you will come to know. Then for the solvers you have, so now these are not coupled solvers, okay, these are pressure based solvers. So, you have this pimple scheme, and then for this P, U, E and H you have this P by CG stab, and then you have PCG for rho. So, these are the solvers for the pressure based solver. So, which is out of the scope for this current course, we will not discuss in detail, but I just want to show that you can solve this using pressure based solver also, and these are the basically results that you have for the pressure based solvers. Okay. Same number of grid points, that was row central form, this is the row pimple form. Okay, and here you can see there is no blip like that, but then the accuracy goes down, it is slightly shifted here. So, this is the row pimple form. Okay. You can do the 2D setup also, as we discussed earlier, that you can have solve it. Let us say you can put the, you want to see how the shock is evolving on top and bottom. Okay. So, you have a shock which is going like this, okay, but if you put a boundary condition on top and bottom, okay, like wall, then you will have this shock bondular interaction, the shock will interact with the bondular also, let us say here. Okay. So, that also if you want to observe you can do that, and if you want to compare the results you can just take the value at the center and plot against the exact data, and you will get the similar results as we did for 1D setup, as we got for 1D setup. Okay, one more example I want to show you, this is supersonic flow over a forward facing step. This is a default problem in I think sonic foam. Okay. Yeah, so here you can see foam tutorial, compressible sonic foam, laminar, forward step, and this is a simple problem, but the results are, I mean, flow features are quite complicated. So, you have a step, it is called a forward step. So, flow is coming and then it sees a step, and because the flow is supersonic, it will develop a shock, a detached shock, right, and the Mach number is 3, okay, and pressure is 1 Newton per meter square. So, how do you set up the problem? First is you have to make a grid. So, you, I think there is a default grid in block mesh that you can use, making 3 blocks 1, 2 and 3, and you can accordingly decide the number of grid points in each of these, okay. And on the sides you have basically empty boundary conditions, okay. So, it is a 2D problem, right. So, here yeah, one thing I want you to note that in the default solver they use u equal to 3, the Mach number is also 3 and u is also 3. How is that? That means they have chosen a is equal to 1, the speed of sound they have taken as equal to 1, okay. In order to get the speed sound equal to 1, so speed of sound is a equal to square root of gamma r t, right. So, it has to be consistent, right. So, they have taken t is also equal to 1. So, t is also equal to 1, the a equal to square root of gamma r means 1.4 r, okay, is equal to 1. So, r will be 1 by 1.4, okay. So, that will be basically 0.7143, okay. So, this is a specific gas constant, okay. So, you know the relation between specific gas constant and the universal gas constant. The universal gas constant is basically this 8314.5, okay. This is universal gas constant joule per mole Kelvin, okay. But in CFD we do not solve in mole, we solve in kg. So, what you do, you solve, you convert it to joule per kg Kelvin, and then we say air has the mass of let us say 20, around 29, okay, kg per mole. So, we divide it, this is my R universal, let me call it R u, you want to call, get R specific gas constant, this will be R u by mm, okay, which is the molecular mass of the air. So, this will be 8314.5 by 29, that gives you around 287 joule per kg Kelvin, right. So, that is how we convert from the mole to kg, right. So, this is the called the specific gas constant and this is a value which is fixed, right. So, if you take this universal value of 8314, then you can find out what is the molecular mass that we are talking about, what is the gas that we are using to get the speed of sound is equal to 1 for the temperature equal to 1, right. So, then you, if you do that, you will get a ridiculous value of kg per mole mass, which is 11640, but this is consistent if you want to use like this. If you do not use this, then you are solving for some random gas which does not give you a equal to 1 and you cannot use a u equal to 3. So, this is one way of setting it up, but you can set it up completely different way. You can have a proper ideal gas, let us say air, and then accordingly you have to calculate A, accordingly you have to calculate U and so on and so forth. Okay. So, all approaches are perfectly fine. So, this value has to be used here in the molecular weight. Okay. And this is also a laminar problem, sorry, Euler problem. So, viscosity is 0 and these are some of the boundary conditions that I have talked about. This is the inlet, fixed value u is equal to 0, u equal to 3 and v and w are 0. Okay. And then you have this is something called inlet outlet. It is a mixture between the 0 gradient and the extrapolation, sorry, the value that is specified here, okay, which is 3, right. So, that is kind of Robin boundary condition here. Then we have the symmetry plane and top and bottom. So, we have top and bottom that we have at the symmetry plane, and then you have there is a slip condition in the obstacle, okay, and finally, you have empty. So, why slip? Because we are solving the Euler problem, and this is how your solution will develop. So, because of this body, okay, the detached shock will develop and which is convert to an oblique shock, okay, and that it will get reflected from the top, okay, and then again it will come, it will get reflected and there will be an expansion fan which will form here, right. So, this is structure you can see, okay. Yeah, this is a kind of density gradient magnitude showing the same thing, basically the shock structure you can see here. Okay. So, this is where we will stop, and in the next class I am going to discuss little bit about some advanced topic which are called the shock modular interactions. So, right now you have solved all the problems using Euler condition, there is no viscosity. As soon as you have the viscosity, the shock will interact with the viscosity, okay, and some more complex flow features will develop. So, we will discuss that in the next class. Thank you very much.